Okay, hi there. Dr. Matthew J. Traum here. The plan in this video is to walk you guys through how to use the Boothroyd and Dewhurst manual handling and manual insertion charts to estimate the assembly time of a simple product that is assembled by hand. Let me preface this all by saying that the way that I normally run these lectures is I like to give you guys 15-minute breaks. So if I happen to go longer than 15 minutes, I will stop right about 15 minutes. And then you guys can go away and take a break, get some food or something, come back, and we'll continue the video for another 15-minute segment until I've said everything that I want to say, and then we'll be done. So we'll go for 15 minutes here, and then take a quick break. So what I've got here is my dot cam. There's my hand. And I've got a couple of bits and pieces of the toolkit that I'm going to use to give you guys this example. So of course I've got my pen so that I can write in multicolors. I've got a caliper, which I'm going to need to take some measurements. So I'm going to turn this guy on and make sure that he is zeroed and make sure that he's set to read in millimeters, which he is. Okay, so that's good. And then I've got a template, which I've uploaded on the course Learning Management System, which I suggest that you guys use when you're calculating assembly time using the Boothroyd and Dewhurst technique. And then sitting on top of the template is my trusty pencil top focus toy. So this is a product that my company used to manufacture, meant for high schools and middle schools and elementary schools. And the original idea was there's a lot of literature that shows that having something to kind of fidget with, like a fidget spinner, seems to be quite good in helping students, particularly with learning differences. So students with like ADHD and autism, for example, to stay focused in class and to sort of keep their hands occupied as they're listening to the lesson. So it's actually good, at least it's shown to be good to have these. The issue, of course, with something like a real fidget spinner is it's basically a toy. And you've got a toy in class, it can be a distraction. And so I came up with these pencil top fidgets here to basically allow a student to hide their fidget spinner in plain sight. So it sits on top of a pencil. You could use the pencil to write, assuming this was sharpened, you could use the pencil to write if you wanted to. And then when you stopped and needed to pay attention, you could go back to fidgeting if you wanted to maintain your focus. And so that was the original intent of this product. And then I actually expanded it so that, so that I just dropped a piece. There we go. So that schools will get 3 parts. They would get the lock nut here. They would get what I call the fidget nut. So it's this 1 inch by 1 inch by 1/4 inch square piece of metal that has the hole in it, and then they'd get a nylon bolt like that. And there's effectively 3 parts, and then they'd get a pencil that it would fit into. And depending on whether we were dealing with an elementary school, a middle school, or a high school, these parts would come in differing levels of complexity. So for an elementary school, the students would just get all 4 parts, and they would just assemble those parts and practice putting things together, taking things apart that were sort of machiny in a way. For middle schools, we would give them the bolt with the hole drilled in it, and the lock nut, and we would give them the fidget nut, but I would not thread the holes, right? So you can actually see there's some threads here on the inside surface there. So I would not thread that hole, and it would be up to the middle school students to, with a tap, put the threads in. And then for the high school students, I would give them the lock nut, I would give them the bolt without the hole drilled in it, and I would give them the fidget nut without the hole drilled in it. And using just a shop press, which a lot of physics classrooms have, the students would be responsible to put that hole in the top of the bolt there, and to put this hole in the nut, and then thread the screws in. So anyway, This was a cool product that was deployed at a couple of high schools. And I used to pass these things out at like conferences, like education conferences, sort of as a giveaway to promote my company, right? So like, for example, you can see here, that's the company's website that would be on these pencils that I would give away. So anyway, the challenge then is to figure out how long it takes to manually assemble this product, which I had to manually assemble hundreds of them, sometimes probably thousands of them, when I was producing a lot for a conference or something like that. So how long does each one take to put together is the key question. So the first thing that we want to do in answering this question is to figure out the sequence of operations. And you as design engineers will have to come up with the best sequence of operations. And in my mind, there's two different possible sequences. And let's talk through kind of why one is potentially better than the other. So the first sequence goes as follows. So I'm using my left hand. This is my non-dominant hand, and I'm going to pick up the bolt. And then I'm going to use my right hand, my dominant hand. I'm going to pick up the fidget nut, and I'm going to thread the fidget nut onto the bolt without cross-threading it. There we go. Okay. So now I've got that threaded on there. And so now I've got a sub-assembly which is made up of the nut and the fidget nut and the bolt. And here is where I have two options. So the first thing that I can do, which is maybe more logical, is I can, with my dominant hand, grab the lock nut, put it on there, screw it into place, and then pick up the pencil and put the pencil into the hole. Now, here's the thing with this is that this lock nut has two purposes. The first is as I'm fidgeting, it essentially serves as a bottom stop that prevents the fidget nut from just spinning off the bottom of this thing. So that's one purpose. But then the second purpose is that I tighten this down pretty good, and I really just need to tighten it by hand, but if I tighten it down pretty good, the nylon of the bolt is a little bit compliant, and if I tighten this guy down, the nylon will actually cinch down onto the pencil, and now I can pull on this pretty hard, and the pencil's not going to come out, right? So this is now sort of semi-permanently fixed onto the pencil, whereas if I loosen this guy up, there we go. I'm just loosening it by hand. If I loosen it up, the nylon again is compliant, and so now the nylon has relaxed a little bit, and now I can just pull the pencil right out, right? So there's actually an additional step here at the end, which is I want to, by hand, tighten this nut down onto the nylon bolt so that it gets a good grasp on the pencil. And so because there's that extra step, what I want to do, instead of the sequence of events that I just showed, right, which is I got here, I picked this guy up and put him on, then I put the pencil on, then I tighten down. I want to do that tightening all in one set of processes, all in one step. So I'm going to start from here, right, which is the same for both processes. I'm now, instead of picking up the nut, which is what I showed last time, I'm going to pick up the pencil. I'm going to stick the pencil into the hole. And now with my dominant hand, I'm going to pick up the nut. I'm going to put the nut over the pencil, and I'm going to do the tightening step all in one process, right? So now it's finished, it's tight on there, and that prevents me from having to put the nut on, slide the pencil in, and then do the tightening process. So it is important as a design engineer for you to sort of think through the sequence of steps to try to reduce the number of steps to as few as possible when you're going through this exercise. So now having done that, now that we know the sequence of steps that's the fastest, we can run through how to calculate what the assembly time is actually going to be. So let me pull this apart, and I'll demonstrate each of these steps and walk through how to fill out this table as we walk through it. Okay, so I've got it disassembled into my four constituent parts. Now, normally in an assembly process, each of these parts would come in a big bin with other like parts, right? So I'd have dozens to hundreds of these nuts in one bin, bolts in one bin, dozens to hundreds of these nuts in one bin, and dozens to hundreds of these in one bin, and then a bunch of pencils in a bin, and I'd be reaching first for the bin of nuts, the bin of bolts, the bin of nuts, the bin of fidget nuts, and the pencil, and I'd be assembling out of these bins. Since I don't have bins, we just sort of have to imagine imagine that they're there. But I'm still going to demonstrate for you that the time that it takes to grab the part. So the first process that I need to do is I need to grab the bolt, this nylon bolt. And so again, I'm going to reach out with my my left hand, which is my non-dominant hand, and I'm going to pick up that part. So what does that process look like on one of these diagrams? So let me move all the pieces out of the way and I'll show you. So that's going to be a handling process. There are basically two different processes. One is a handling process, which is I'm reaching out to pick something up. The other one is an insertion process, right, where I have the parts picked up already and I'm putting one part into another part. So that's insertion, and just picking up a part from the bin is handling. And so what I'm going to need to do here in this column, the first step in my process is going to be a handling process. And actually the second step in my process is also going to be a handling process. And it's always going to be that way, right? Because you always need to start by picking up one part, picking up another part, putting them together into an insertion. And so the third step in my process is going to be I. So I'm going to just fill those out right there to remind myself of what I'm doing in what order. Now, the first thing that I have to figure out is for a handling process, the angle of symmetry, the alpha angle of symmetry, which is the angle orthogonal to the insertion direction. So if I look at my my bolt here, I'm going to point my pencil or my pen in the insertion direction, right? That's the insertion direction. And so the axis that's orthogonal to the insertion direction is one that goes into the page or up towards the camera. And so alpha, that angle of rotation that I'm talking about for this column, that alpha is going to be rotation in this direction, right? So if I'm rotating around that axis that's orthogonal to the insertion, that's alpha. So there's rotation in alpha. Now, these are angles of symmetry, right? And my insertion process basically eventually, my insertion process is basically going to look like that, right? So how far around do I need to rotate this guy to get him back into an orientation that I can insert this piece into this piece, which is the one that I'm eventually going to do for the insertion step? Well, let me just sit this like this so that you can see. I'm leaving my pencil here to just remind us of what the insertion direction is. If I turn this guy 90 degrees in alpha, well, that's not going to work. I can't insert it that way. If I turn it 180 degrees in alpha, that's not going to work. I can't insert it that way. If I turn it 270 degrees, that's not going to work because I can't insert it that way. Whoops. And if I turn it a whole full 360 degrees once all the way around, I've now restored my ability to do this insertion process. That's the symmetry condition, right? So I got to rotate this guy all the way around to achieve symmetry. And so what that means is that my alpha angle is going to be 360 degrees, 360. All right. Beta, what's beta? Well, I've got alpha figured out, so let's talk about beta. Beta is an angle around the axis of insertion, right? So again, I've got my pen here pointed in the axis of insertion. When I do my insertion process, it's going to be in that direction. So beta is rotating about that axis, which is rotation this way, right? So I'm rotating beta. Okay, so what does that mean? What's my beta angle? Well, it turns out, yes, okay, this thing has threads on it. And if you're familiar with threading things in, you know that you sort of have to orient things so that the threads line up just right so that you can do the insertion. But for our purposes, the twisting associated with the threading process, the time to do that is associated with the insertion step, not with the handling step. And so when I pick this up and prepare for the insertion, it actually doesn't matter how this thing is oriented in beta, so long as I can get it there and then start twisting it, I'm going to be fine for my insertion to work. And so for our purposes, the beta angle is 0. And then if I add them up, I get 360 plus 0 is going to be 360. And that gets me to the point where I need to look up the handling or insertion code for this process. But hey, I'm right at 15 minutes, so I'm going to stop, give you guys a break, come back, and we'll pick this up right from where we left off. So see you in a moment. Thanks.